So now let's look at our two aperture diffraction pattern. But now let's consider the fact that our apertures have a finite size. So we're going to have both diffraction and what we call the double aperture interference. So our apertures are a distance d apart, and we have a screen out here, P. And now what we're looking at is the interference pattern that we see on the screen. Now, I would like to draw my screen like this. So here's my screen, and here's y equals 0. Now, we showed that the intensity is going to go like some amplitude times a cosine squared of a function 2 pi lambda d over 2 sine of theta, where our angle theta to the point. And what that gives us for, this is the intensity for two apertures. And what we have here is a cosine function. So I'll just try my best to draw this cosine function. And what we would see if we had no diffraction whatsoever is just a band. This is a minimum. This is a maximum. So what you might see on the screen is a band where it's very dark, and then it gets to the minimum. And likewise, a band, a 0, starts to get darker and gets a little lighter. And so that would be the pattern that we would see on the screen. So this is the intensity that you see with two apertures. Now, the intensity that you see for diffraction looks a little bit different. And that intensity, so this is the diffraction. This is the interference of 2. There, we have also some coefficient. But now the function is a little bit more complicated, and it depends on this width, sine of theta, and it goes like that quantity on the inside, a over 2 sine theta squared. If I drew this one in the same way, notice that the difference is, remember, our diffraction minimum. So let's just qualitatively remind ourselves for the diffraction, the minimum was where we had m times lambda times L over A. And the maximum from the interference was y max was m lambda L over D. And D is much bigger than A. So the interference maximum, we could call this on the screen the distance where m is 1, so that would be lambda over d. This distance is, d is bigger than a, so these interference maximum are very close together compared to the first diffraction minimum, because a is a smaller quantity, so the diffraction minimum is a much bigger quantity. And so we'll kind of draw this diffraction curve like that. And this is the first diffraction minimum at the value lambda L over A. And so what we actually see on our screen when we're combining diffraction and interference is the idea that the intensity is the product of these two. And so we would have some coefficient a times cosine squared of the quantity in the parentheses, 2 pi lambda d sine theta, times the diffraction envelope, this quantity which was sine squared 2 pi lambda a, that's a factor 2, sine theta over 2 pi lambda a sine theta squared. Now, if we draw that out, one way to think about it is first just draw the interference maximum, the interference pattern. So we have this cosine squared function. And now draw the diffraction envelope. I'll try to draw that something like this. So here's our first diffraction minimum, and the envelope goes like that. So the actual pattern that we see, now of course these two things aren't necessarily in scale, is when you multiply these two factors together, you're taking this pattern and multiplying it by our diffraction pattern. And when you do that too, and I'm going to erase the two in a moment, but I'll get something that will look like this. There'll be these minima, but they won't at maximum, but the maximum won't have the same height because diffraction is cutting down the intensity there. It comes down again, here, there. Now this is the interesting one. This point should be an interference maximum, but it's a diffraction minimum, so there's no intensity because we're multiplying it by a 0, and then this pattern continues off like this. So what you see is, now let's just make that envelope like that, and let's get rid of the interference cosine squared function, which was uniform. And I'm just trying to make this look like this is the interference pattern, the intensity that we see on the screen. Now, from this intensity pattern, we can notice the following very important fact. Right here, let's count interference maximum. This is m equals 0, m equal 1, m equal 2, m equal 3. And that's missing, because this m equal 3 interference maximum corresponds to the first diffraction minimum. And so we have the condition that the first diffraction minimum set the diffraction minimum n1, lambda L over A, this is the 1, 2, 3, 0, 1, 2, third interference maximum, 3 lambda L over D. And so we can conclude that the distance between our two apertures is 3 times the width of a single aperture by analyzing this intensity pattern. And that's combining diffraction envelope with the interference pattern of intensity. And that's how we can determine the relationships of distance between the apertures and the size of each individual aperture.